Okay, this is 4.1, related rates. Hello. This is going to be different because you'll be seeing me virtually, but hopefully you will still be getting the same experience as you would in class, as I will be using the PowerPoint and recording the solutions on a whiteboard. I'll forewarn you, my handwriting is horrible on this whiteboard. I'm writing on an iPad, and I find that it's not very good. My handwriting isn't good at to begin with, but on this thing it's even worse. So if you can't read it at all, just let me know and I can always send you a paper copy. All right, let's go over to the PowerPoint. So don't forget, this week you do have your exam 2 to take through WebAssign. Okay, it's open on Sunday because I wanted to give you guys a weekend today, and it is due by Wednesday, this Wednesday, whatever the date is, the 1st, April 1st by 11:59 p.m. And you are required to upload your work. So make sure that you're prepared in doing your work out, which I will explain some more in my intro video, which is posted in the announcements. If you haven't listened to that video yet, make sure you listen to that one first. Okay, so we have 3 word problems that I wanted to go through today for related rates. The first one, air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So there's important pieces to this word problem. One, we have to recognize that we are inflating a balloon that is of spherical shape. Okay, so normal shape balloon. Spherical technically is an oval though, so think of like a basketball balloon. And we know that the volume is increasing, which means everything else is increasing. Your circumference, your diameter, your radius, everything. And we want to know how fast is the radius increasing? So this is how we know what we need to find the derivative of. We need a derivative for the rate of, for the how fast the radius is changing. So let me switch to my whiteboard. There we go. Okay, so what do we know? What we know is, again, handwriting not going to be that great at all. Okay, let's try this again. That was not working. What we know this is going to be interesting. Okay, we know that the change in volume over time, okay, so the change in volume over time is equal to 100 cubic centimeters per second. Okay, that was given. So that's not something we had to find out. But what we're looking for, what we want to know, we want to know is how fast the radius is changing. So that would be, how fast is the radius changing, the derivative of the radius over the derivative of time. So how fast the radius is changing over time. So this is what we want to find, but this is what we know. So what else do we know about spheres as they are growing, as the volume is growing? Well, we know that the volume of a sphere, which we derived once we learned implicit differentiation, is equal to 4/3 pi r cubed. That is the volume formula for a sphere. So it makes sense that this is where we should start if we're working with a geometrical object that the volume, or if the volume is increasing. It makes sense to use the volume formula of that object. So let's page. Clear all. There we go. And let's start with this formula. So we have V is equal to 4/3 pi r cubed. So the first thing that we're going to want to do is implicit differentiation. We want to take the derivative of each side of the equal sign. So we are going to take the derivative of the left, which is dv dt. Okay, so we're taking the derivatives with respect to time. So the volume is changing at this rate, and it's equal to now the derivative over on the right side. If you look at the right side of the equation, you have 4/3 pi. Those are all numbers, so that's just a coefficient. So we're going to take our exponent and do the power rule. So we're going to take the 3, multiply it down in front, come back up and subtract 1. So that will give us 3 times 4/3 pi r to the 3 minus 1, which that simplifies to the 3's cancel here. So we have 4 pi r squared is equal to dv dt. Ooh, missed one part. So because r is a variable that is changing, we do need a dr dt. So it acts like a function. Like when we were doing implicit differentiation, our y's were functions while our x's were variables, and our y's needed a y prime. So that's the same thing here. Dr dt is the same thing as r prime, but we're using a different notation for the derivative because we want to emphasize that these derivatives are taken with respect to time. Okay, so now let's talk about what we have in this formula. We have what we need to find out is equal to, so we need to find the value of dr dt. We already have the value of dv dt. If you recall, we were given that value at 100 centimeters cubed per second. So we have that value. We know the radius, okay? So the radius was given in the problem. They told us that we had a diameter of 50 centimeters. So that would make the radius, if you recall, the radius exactly half of the diameter. So the radius is 25 centimeters. Okay, so we have r. We can replace r with 25. We have dv dt, which is 100. And we need to solve for the only thing we don't know, which is dr dt. So again, let's take a look at the process of this problem. The first thing we did was we recognized what we have, what's given, and what we're trying to find, because that makes it easier to remember which variable you do not want to put a number in for if that's what you're trying to find. We then took a look at the shape that was changing and found a formula that made sense for that shape, so our volume formula. We then took the derivative of both sides. Okay, so that's here. We took the derivative of both sides, and we treat every variable that's changing with as a function. So volume is changing as the balloon increases, hence dv dt. Radius is changing as the balloon increases, dr dt, and there are no other variables here, so we don't have to worry about determining other variables and whether they're constant. There's times where in the next problem we're doing, a ladder is going to be sliding down the wall. Well, the ladder is a constant. The length of the ladder is not changing, and so that one would not get a d ladder dt, whatever variable we're going to use. Okay, so then once we found the derivative, we then identify the variables we're not solving for we should know something about, leaving us with the variable we need to find as the only unknown value. Okay, so now let's plug in what we know and let's finish this problem. So we know, let's write down our formula again. We have dv dt is equal to 4 pi r squared dr dt, where dv dt is 100 and our radius is 25. And we are solving for dr dt. So now we need to solve for dr dt. So if we square 25, we get, we square 25, 25 times 25, we get 625. And then we have to multiply that times 4, and we get 2,500. So right now we have 100 equals 2,500 pi dr dt. Notice I'm not multiplying by pi because the moment we do that, we are automatically going to be approximate. So I wait to the end to do that. So now we need to divide by 2,500 pi on both sides. Let's write this on the board. Okay, so we have 100 divided by 2,500 pi is equal to dr dt. Okay, and because we are in the units of centimeters and seconds, this would be labeled centimeters, and this is the exact answer. But if we divided this out, 100 divided by, and make sure when you put it in the calculator, it would be 100 divided by, in parentheses, 2,500 times pi. You need the parentheses because in order of operations, it's going to go left to right with division and multiplication, and it will divide the 100 by 2,500 before multiplying. That's not what we want. So this comes out to be approximately 0.0127 centimeters. Ooh, centimeters per second. All right, centimeters per second. So the radius is a 2D, volume was 3D, which is why it was centimeters cubed. But this isn't area, this is just the straight line, the radius changing, so that's centimeters per second. So this is the answer to the problem. How fast is the radius changing? dr dt. It's changing at a rate of 0.0127 centimeters per second. Okay. Now, if I go back to the PowerPoint, let's look at our second example. So our second example is that ladder problem I said was coming up. So we have a ladder 10 feet long that rests along a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So when you read this problem initially, it sounds as though that the top of the ladder should be sliding at the same rate as the bottom of the ladder, but it doesn't work out that way. So let's take a look whiteboard for this problem. Okay, so we know we have a 10-foot ladder. We know that at the bottom is sliding out at 1 foot per second, and the bottom of the ladder is 6 feet away from the wall. So let's draw a picture so that we can see what this looks like. Switching over to my whiteboard. Okay, so we have a wall, and we have the floor. And we have this ladder. So here we're going to demonstrate that the ladder is 6 feet away from the wall at the bottom. It's a 10-foot ladder. Okay, it's sliding down on the vertical side here. So we're sliding down all this Y, and we'll call the bottom of the ladder is sliding outwards. So we will call this change in distance X. We also know that it's outwards at 1 foot per second. Okay, so here's a picture that shows what's happening. Pictures are really helpful because in some cases, the equation to start with is not that obvious. So in the last example, we were working with a sphere, a geometrical object. Okay, so we know what a sphere looks like. We know the volume formula for a sphere, and that led us to using our V equals 4/3 pi r cubed. But in this particular example, there isn't a geometrical shape, or at least not an obvious one, until you draw it. So when I draw the scenario is when I see, okay, this is a right triangle where I have 2 legs to the right triangle, the X and the Y, and I have the hypotenuse, the ladder. So I know that a squared plus b squared is equal to c squared. The Pythagorean theorem applies to right triangles, and I feel like this might be necessary here. So I take a look at this beginning formula, and there's some things I have to think about. I have to think about which one of these variables should I be considering to be changing variables, varying variables, and which ones of these are not growing or changing. So A is one of these two sides. Let's make it X. So we have X squared. The bottom of the ladder is sliding out. Okay, so it's sliding out to the right, which means that the distance from the wall is changing. So we will need a dx dt when we derive that one. B is the vertical slide, which is denoted by y, the distance of the top of the ladder to the floor, and we do expect that to be changing as the ladder is sliding. So when we derive the y variable, we will treat it as a function and create a dy dt. Now, C is the 10-foot ladder, and as this thing slides, the 10-foot ladder remains 10 foot, which means that it is constant. As the ladder is sliding, that variable does not change, which is why, and that is the only reason why, we can put that number in prior to taking the derivative. So keep in mind, numbers do not get substituted in prior to taking the derivative unless they are constant, meaning they do not change as the action is happening in the problem. So now let's take a look at our starting equation, which is x squared plus y squared is equal to 10 squared. And now that we have our equation, we will follow our steps. Our steps now are to take the derivative and treat every variable that is changing in the problem as a function. So we have 2x dx dt. Remember, we are using this notation because we are emphasizing that we are taking the derivative with respect to time, plus 2y dy dt. 10 squared is just 100. A derivative of a constant, you guys remember, is 0. Okay, so now let's talk about which one of these derivatives am I actually trying to find, and which one should I already know something about. So the question, if I go back to the PowerPoint, which I'm not going to switch back, but you guys could look back at the question, and it asked me, if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, so the bottom of the ladder is sliding and we know how fast, we want to know how fast the top of the ladder is sliding. Okay, so that means that dy dt is the 1 foot per second because we are, oh, sorry, that is not correct. Let's do that. Other one. dx dt, here we go. Dx dt was the one that we set for the horizontal, so that's the bottom of the ladder sliding out. So we know that that's 1 foot per second. dy dt is the downward shift. So this was the rightward shift. This is the downward shift, and this is what we're solving for. We want to know how fast the ladder is sliding. So we'll substitute the 1 in for dx dt, and we are solving for dy dt. So let's do that. So we have 2x times 1 plus 2y dy dt is equal to 0. Now I realize once I get to this point that I only know one of the 4 variables that were here originally. I still have variables that I need to find. For example, I need to know what x is and y is, so that the only thing I'm trying to solve for is dy dt. You only can have one unknown in one equation. So if I go back to my picture, I know that the hypotenuse was 10 feet. And this is y. Nope, sorry. This was y. And this was x. So is it possible for me to find x or y, or do I know one already? Well, if I go back to the problem, it asked me specifically how fast was the top of the ladder moving down the wall when the bottom of the ladder was 6 feet away from the wall. So we do know x. We know x is 6. So this is going to be 6. So if I use the Pythagorean theorem, x squared plus y squared is equal to c squared, I can solve for y. So when x is 6, I need to know what y is. So we have 36 plus y squared is equal to 100. Subtract 36 on both sides. You get y squared is equal to 64. And then if you take the square root of both sides, okay, so we have y squared is equal to 64. Take the square root. I don't need the plus or minus because we're talking about the length of a side here, so a negative distance doesn't make sense. And we have y is equal to 8. So now if I go back to my formula, I have 2x dx dt plus 2y dy dt is equal to 0. So now I'm going to make my substitutions. I have 2 times x, which is 6, times my dx dt, how fast the bottom of the ladder is sliding out against the wall, and that is 1 foot per second, plus 2 times y, which we just calculated to be 8 in there. We are trying to solve for dy dt, so we shouldn't know a number for that yet. This is all equal to 0. So 2 times 6 times 1 gives us 12, plus 2 times 8, which is 16, dy dt equals 0. Subtract 12 on both sides, we get 16 dy dt is equal to negative 12, and divide by 16 on both sides. So we get dy dt is equal to negative 12 divided by 16. Now let's reduce this so it's a little prettier to look at. That's negative 3/4, and we would label this feet per second. Now, if we were in class, I would then be asking you guys, why is it negative? And is that okay? And hopefully one of you would be able to tell me that negative is okay because it tells you the direction in which the movement is happening. The ladder is not moving up the wall, it's moving down the wall. Hence the negative tells us that the object is moving downwards at 3/4 foot per second. Okay, now if we switch back to our PowerPoint for our third and final example. Our last example, car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So, you guys all know I'm a visual person. I am going to start with a picture. Pictures make a heck of a lot more sense to me than reading English paragraphs. So it told me that car A and car B are moving towards each other towards an intersection. Car A is moving west. So if I draw a quick little compass here, we have north, west, east, and south. Okay, remember where west and east are because it spells west, W-E. That's how I remember. So if car A is driving west, it means it's moving to the left. It's moving towards the W, to the left. So we have car A. We draw a car. No judgment on my car. Drawing. Car B was said to be traveling north. So to be traveling north, you need to be traveling upwards. Okay, so this is car B. Another headless car here. And we have, let's say, X distance from the intersection, and Y is going to represent the distance away from the intersection for car B. And in order to create a shape, remember, we need an equation. The distance between the two cars, so this dotted line represents the distance between A and B. So that is the distance between the two cars. We'll label that distance Z. We also know how fast these cars are moving. So car A was said to be moving 50 miles per hour, while car B is moving 60 miles per hour. So car B is moving faster than car A. And we want to know that at what rate are they approaching each other when car A is 0.3 miles away from the intersection. Okay, and car B is 0.4 miles away. Now, this is our visual. I can see that this visual gives me a shape. It gives me a right triangle with a hypotenuse and two legs, which allows me to come up with the equation x squared plus y squared is equal to z squared using the Pythagorean theorem. Now again, I want to discuss which ones of these variables are actually changing as this problem action moves on and which variables remain constant. So x represents the distance from the intersection for A, and that's changing. Car A is moving towards the intersection, which means the distance away from the intersection should be getting smaller. Same with car B's distance. So Y is changing because car B is moving towards the intersection, and therefore the distance from the car to the intersection is also getting smaller. Okay, so X and Y need to be treated as functions. Z is also changing. The distance between the two cars, you can see as the cars get closer to the intersection, their hypotenuse or their distance is going to get smaller and smaller. If you see by these red lines, as they get closer, the red line gets smaller and smaller. So Z is also changing. So right now, X, Y, and Z are all changing variables. There are no constants. So we are going to treat them as such. Let's clear this out and let's take our derivative knowing that they're all going to be treated as functions. So x squared plus y squared is equal to z squared. So we have 2x dx dt. Notice I did not plug in any values into the variables that are changing. All of these we have decided we're changing, and that's why they remain x, y, and z until we are done taking the derivative. Once we've taken the derivative, we can go back and start making substitutions. Okay, so our goal is to find out how fast is the rate of the cars approaching each other at a certain place in time. Okay, so remember, this is how fast they're approaching each other. So this is what we're trying to find. We don't want to substitute value in for dz dt, but that means we should know something about x, dx dt, y, and dy dt, and z at the moment of time they're asking us about. So what do we know about dx dt? How fast car A is moving? Well, we know that's 50 miles per hour. dy dt is how fast car B is moving, and that was 60 miles per hour. So we have those. Now we need x, y, and z. Now we were told x. They told us that they want x to be when car A is 0.3 miles away from the intersection. Y is going to be 0.4 miles away from the intersection. And because this is a right triangle, now that we have x and we have y, we can find z by doing the Pythagorean theorem of 0.3 squared plus our x, 0. iPad does not like points. 4 squared is equal to z squared. We will solve for z. So let's do that. So we can find z. So we have 0.3 squared plus 0.4 squared gives us 0.25. If you put that left side of the equation into your calculator. Square root both sides. Remember, we don't have to worry about the negative radical because we're talking about distance, so that would not make any sense. And z is 0.5 is our hypotenuse. Okay, so now we have x, we have dx dt, we have y, we have dy dt, and we have z, and we are ready to make our substitutions so we can find dz dt. So let's do that. Okay, so we have 2 times x, which is 0.3, times dx dt, which is 50 miles per hour, plus 2 times y, which is 0.4, all right, times how fast dy dt that car B is going. 0.4. Oh, that's better. And car B was going 60 miles per hour is equal to 2 times z, which we just calculated to be 0.5, times dz dt, which is what we're trying to solve for. So we put 2 times 0.3 times 50 in our calculator and we get 30. 2 times 0.4 times 60 in our calculator and we get 48. 2 times a half gives us 1 dz dt. 30 plus 48 gives us 78 miles per hour for how fast the cars are approaching each other at that exact moment in time. There's our answer. Okay, hopefully you guys found this video helpful when trying to decide how to solve these related rates problems. And I hope you guys don't have too much trouble with your first test online. And I'll give some pointers in my intro video. Okay, see you guys next week.